Yesterday we were talking about the stack, which is not peculiar to the 851 family. It's a well-known data structure provided by many processors. The crucial thing of the stack is one of these things, a last in, first out area of memory. And all we're doing is using some of the internal data memory to store the stack. There are two explicit instructions that operate on the stack: push to add something to it, and pop to take something out of it. And you always push and pop to the top of the stack. The push operation works by adding one to the stack pointer and then placing the information in that location. The pop subtracts one from the stack pointer after taking something from the location. So you're adding one to the stack pointer and storing, or extracting and then subtracting one from the stack pointer. The stack pointer defaults to location 07 in the internal data memory, which happens to be register R0 of register bank 1. So if you happen to be using register bank 1, you might encounter some difficulties because as you're using the stack, you're going to be overwriting the registers in register bank 1. If the stack gets even bigger, you'll start overwriting the registers in register bank 2. If it gets even bigger, you'll overwrite them in register bank 3, and so on. Take a little aside here, because I prepared, if I can find it. This program, by the way, is the, oops, that's not one, go away. How do I know? Go away. Silly thing. About half an hour, it will take my advice. This is this program called MCU 8051, which is available free. You can download and install. It definitely runs under Windows 7, XP, things like that. It might also run under Linux, I'm not sure. And it's basically an environment where you can write assembly language for the 8051 family, and you can also simulate it. It's got a simulator built into the environment. I'm sorry I can't really make it any bigger, so for those of you with bad eyesight, also I can suggest as you kind of come closer. It can also allow you to program in C for the 8051, and it will create the appropriate machine code converting from C to machine code, but I've never tried it. So if you want to do that, you're welcome to, but you're on your own. Okay, so this is the program that I've written. It's a very silly program, but it allows us to see what's going on with the stack pointers, and maybe clears up one or two call them problems that we may have encountered yesterday. So what I've done at the top is I'm saying put the value 20 into the stack pointer. I'm then explicitly setting register bank 0. And remember, in this course, in terms of an exam or something, you would be expected to know how you switch between the different register banks. So we're using 2 bits from the program status word, bit 3 and bit 4, that determine which register bank is active. So I've written clear PSW.3, clear PSW.4. I don't know if I can make that any bigger. What does that do? No, that's a search option.
I think you have to just change the font size, that's all you can do.
What can I do?
I think all you can do is change the font size.
Yeah, I'm just wondering if there's a configure. Yeah. Fonts. Oh yeah, well done, thank you. Right, should we try 15? Or 16? Okay, bit bigger?
Yeah.
Alright, bigger.
You can see a problem.
Those out.
You can see it
I
properly.
think that's people are really going to get it. So, at the start of my program, now I've been a bit naughty here, I haven't actually said, it actually doesn't complain when I compile this, as far as I remember. I haven't actually said where this code should go in the memory. I really should precede this with org 00 as a directive. So what I could do is in here, add something like org to basically explicitly state this code I wanted to go into the processor starting from that location. Anyway, the first line of my program is to move something into the stack pointer, then to select register bank 0, and then I'm going to write certain values to, if you like, the registers in register bank 0. And you can see in register 0 I've written 1, in register 1 I've written 2, and so on. So that's, after that I'm going to switch to register bank 1 and carry on writing values. Okay. So notice I'm still talking here about R0, but we're not talking about the same R0 because just prior to that I switched register banks. So what you should see is when I'm writing these values, the previous values, the other register R0, won't be affected. Having written everything, if you like, I've written 8 values to register bank 0, I've written 8 values to register bank 1, I'm then going to start playing around with the stack. I'm going to push 0 onto the stack. And what you'll see is it's not the current R0 that'll go into the stack, it will be 0 because the number following the push is a direct address. So it doesn't matter which register bank selected, that will be location 0 in the internal data memory. Then I'm going to push 8. And then I'm going to fiddle around with some of these registers, and then I'm going to do some popping. So let's see what the last part of it does. So I'm going to put something on the stack, and we can see how the stack behaves. And then I'm going to overwrite R0. Now, the version of R0 that will be overwritten will be based on which is the currently selected register bank. Now, at that point in time, I'm still in register bank 1. So when we rewrite R0, we should see it's the R0 in register bank 1 that gets written 0. Yeah?
Instead of changing the bank, why can't you just protect the registers?
You can. There's nothing to stop you explicitly referring to the registers with their direct memory address. The problem is the instructions to do that they're bigger. Because you've got the instruction, I want to go to a direct address, and then you've got to fetch the whole byte of the direct address you're talking about. So it takes 2 fetches from the code memory, whereas some of these instructions will only require 1 fetch from code memory.
That's good.
So you can always do what you're suggesting, but it's not the most efficient.
It was good, but
So having blanked, written 0 to one of the R0s, we're going to take something back off the stack, we'll see how that works, and then we just loop around, and off we go again. So I'm going to run this now. Now I'll read out things, it might be a bit small down here, I don't know how I can make, I suppose I can make that bigger. Let me try. Configure simulator maybe? No, it's not the right. Configure. I don't think it's going to, I think we won't worry about that too much. Okay, so anyway, so to run, I'm going to compile it, which is this button. And you can see it started here, there's no warnings, no errors, so it's happy with my code. That's a relief. It's generated a number of files as a result of this. One of them is a hex file, which just doesn't mean that it's hexadecimal values. It's specially encoded in Intel hex format. That's a version of my program that a programmer could understand to actually write the information into the code memory in the device. Okay? So now that it's compiled, available, we can now go to the little rocket icon, this thing up here, and actually run the program. So now it's running. The green bar shows you the current line of the program that it's on, and we can step through the program line by line and see what happens. So the first thing we're going to do is to move the value into the stack pointer. Now the stack pointer, we could actually look for it if you're interested. It's down here is the lower half of the internal data memory. This doesn't actually show you the upper half of the internal data memory, pity, but it is available to us. You can see what's going on via this little tab, which shows us what the special function registers are doing. So if I go down here, you can see that internal data memory location 81 hex contains the value 07. That's because the stack pointer, when you switch the power on, has the value 7 in it. Okay? So let's step to the next line. Little step thing. Having done that, what I hope to see is
Did you see it there?
the stack pointer no longer has the value 7 in it, it's changed to 20 hex. Okay? So now the stack, we've reconfigured it so that the base of the stack is at location 20 hex in the internal data memory. That will not be the first location we write to. Because remember, a writing operation to the stack, you add one to the pointer before you do the write. Okay, so we're now going to select register bank 0, and what you would see is in the program status word here, some values changing. But in this case, we're writing zeros with zeros, so you're not going to see anything exciting. I'm afraid, not yet anyway. So step that. And then we're going to start loading up values into these registers. Now because we've selected register bank 0, I expect it'll be, this is the internal data memory, location 0, location 1, 2, 3, 4, 5, 6, 7, location 8, 9, A, B, C, D, E, F, location 1, 0, 1, 1, 1, 2, blah, 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 1A, 1B, and so on. Sorry, 1A, 1, 8, 1, 9, sorry, yeah, 1A, 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 1B, 1C, 1D, 1E, 1F, and so on. So let's do that quickly. And you can't see it very clearly because of the colours, but you can, for those of you with super good eyesight, effectively as I'm running this, you can see internal data memory location 0 has got the value 1, internal data memory location 0, location 1 has got 2, internal data memory location 2 has got the value 3, and so on. Carrying on stepping. Whoops, didn't do that. Right, now, this is how I'm choosing register bank 1. So I'm going back to the program status word, and I'm fiddling around with a couple of the bits. So bit 3 is the least significant bit for the register bank address, and bit 4 is the most significant bit. So if I was to set them both, I would be selecting register bank 3. If I clear them both, I'm selecting register bank 0. In this particular case, I'm setting the least significant bit and clearing the most significant bit, which is the same as selecting register bank 1. So we do that. And then I'm going to repeat the instructions I had before, except I'm going to write different values. And I'm just doing this to prove to you that although I'm writing to R0 now, what we hope to see is it not going to the same R0. Now that's what's in the current R0, value 1. So, whoops, I'll do it again. So I've ran that instruction. You can see it didn't go there, it went into here at location 08. Because we're in register bank 1 now. And register bank 1, R0, is at location 8, and so on. So I'll quickly whiz through that. So far now, I've written 8 values to the first register bank, another 8 values to the second register bank, and so far we've still got register bank 1 selected. And I've initialized the stack pointer to point to location 20 hex. 20 hex is actually here. And let's see what happens when I do the push, whether it's this number that changes or whether it's number 21 that changes, okay? So we're going to push 0. Now, if this meant R0, remember we've got register bank 1 selected. So the value that's pushed, you'd expect it to be 09. But that's not what you're going to see, because what you're pushing here is not register R0, it's direct memory location 0. Okay? So we'll see, which actually has the value 1 in it, I believe. So, next instruction, push 0. So let's see what we got stored. The number 01. Okay? Because what's pushed is not R0 from the currently selected register bank, it means direct memory address 0. And there is only one direct memory address 0, which happens to be register R0 of register bank 0. Whether it's the selected register bank or not, makes no difference. You'll also notice that the location got written to was not location 20, which is where the stack pointer was initialized to, it's location 21. Now I'm going to do another push. I'm going to push the value 8. Now that will be equivalent to pushing R0 of register bank 1, because R0 of register bank 1 sits at direct memory location 8. So I'm hoping to see the value 9 appear in the stack. And sure enough, next to the 21, location 21, at location 22, the value 09 has appeared. You notice I haven't had to do anything manually about incrementing the stack pointer. It's all done automatically as part of the pushing operation. And it all happens in one instruction cycle, so it's actually quite quick. So now so the stack pointer will currently be pointing here, at location 22. In fact, you can prove that because up here it says SP22. That's 22 hex. Right, let's move on down. So, and then fiddling around with the program status word again, and I've now selected register bank. I've selected register bank 0 again. And we're going to do a bit of popping now, but before we do that, I'm going to override R0 with the value 00. And it's just to prove to you that we're no longer fiddling with register bank 1, we're now fiddling with register bank 0 again. So when I blank this value, I expect it to be this one up here that's going to change. And sure enough, that's now got the value, for those of you with brilliant eyesight, it says 00. Okay. And then I'm going to do some popping. And let's see what happens. Now, I'm popping 8. I could pop 0, I could pop wherever I want. The number that follows the pop is the direct memory location you want this information to go to. Now, I want it to go back to where it came from. So this will go back to direct memory location 8. Now, the value that's extracted from the stack is wherever the top of the stack is. So the top of the stack contains the value 9. So the value 9 will go back to direct memory location 8, which will be, where are we? Here. I don't remember clearing that one before. Oh yeah, I've done it, I can see. What I didn't realise was I've actually, deliberately, I've cleared both of the R0s. I cleared one before I did the bank switching, and I did one after. So that's why currently they both register bank 0 R0 is 0. Register bank 1 R0 contains 0 as well. That's what those instructions up there did. So I'm going to pop 8, and we'll see what happens. So when I pop 8, as if by magic, location 8 in the direct memory takes the value that was on the top of the stack. So it's been given the value 9 again. Now you can see that this information at this location hasn't changed. Basically, it's been copied back off the stack. But the stack pointer has changed. The stack pointer is no longer saying 22, it's gone back to 21. So although we've got a number here, this number is not meaningful anymore.
That's it there, I will kill you.
Yes, and that's happened automatically. It took place as part of the pop. The pop itself did it. So what happened was, it was pointing to 22. When you did the pop, it took that value, put it wherever you told it to put it, which is location 8. And then it took one away from the stack. but it's all part of that instruction. You don't see it, you see the result of it. And you'll see it, we can watch it again now. Okay? So currently, the stack pointer has the value 21, which is pointing to this location. And now we're going to do a push, a pop 0. A pop 0 just simply says, take whatever's off the top of the stack and put it in direct memory location 0. Okay? Now, direct memory location 0 is actually up here. It happens to be R0 from register bank R0. So we'll do that, and what we hope to see is the value 1 appear back in here. So, did that, and then, as if by magic, the value 1 has appeared back in here. Now let's look at the stack pointer. The stack pointer's got the number 20 in it. Now, I didn't have to take one away from the stack, that just happens automatically as part of the pop. And then that's the end of the program. The program just sort of jumps around and carries on doing that same silly thing forever and ever. So, anyway, I just wanted to show you that the values that are pushed and popped, the number that comes after them, is a direct memory address. It doesn't matter which register bank is selected for those. Yeah?
Even though stack pointer is 7,
Yeah?
you can provisionalize it anywhere.
Anywhere in the internal data memory. So the biggest value you could put it to is FF. If you then put something on the stack and it's already at FF, it will wrap around to 0, 0.
You really start at 7 anyway, so you have more.
You can, and then you can have a bigger stack. The downside of that is if you do want to use register bank 1, for example, to store some temporary data, your stack's going to overwrite it. So if you as the programmer, you decide where you want it. But yeah, if you want a really big stack, you can put it low down in memory. And then you'd have to remember not to use register banks 1, 2, and so on. Yeah?
I have a question about PSW.
Yeah?
How many bits is it?
It's actually an 8-bit register,
Okay.
but it has other purposes as well.
Okay.
It just so happens that 2 bits in that register, bit 3 and bit 4, are used to determine which register bank is active.
Okay.
And you can see that an instruction like this, move this value into R0, that will depend on which register bank is active, which version of R0 gets that information. Okay, let's close this down
I want to know what the other uses are.
and get back to the...
He'll probably go through them. Have you gotten the email? About we're going to have 4 hours a week now.
Okay, so I think we've probably covered the stack in an awful lot of detail now.
I'm recording one of them.
If you're still not convinced by any of this, there's nothing to stop you from downloading that program and just playing around with these instructions yourself. Just give it a go.
What was it?
It's called MCU. So if you go to Google or something like that, whatever search engine you like, and type MCU
I'm
8051,
thinking of getting a Gorilla.
it will take you to SourceForge, whatever it's called, and then you can just download it for free.
Yeah, right there.
And the guy who wrote it, he still supports it. It's still an ongoing thing. So, if you do choose to download, the nice thing is it's what you're going to be doing in the labs anyway, so you'll be very familiar with the environment. Okay, so I don't think there's anything on that slide that's an issue now. So, and I've also proved to you, I deliberately chose the stack pointer to be starting at location 20. I did that to prove to you that actually this is strictly speaking, and on this slide it's not quite correct. This slide says you're not allowed to occupy memory locations 20 to 2F. In fact, that's just what we've been doing. What this slide should have said is it's not recommended to use those locations because that part of the internal data memory is the only part of the internal data memory that you can fiddle around with that's bit addressable. So it's better to use it for other things. But you can use it as part of the stack if you want. We just did that, and it worked absolutely fine.
Be a rebel.
Right, so the second part of what we did yesterday was about subroutines. I'll come back to that in a minute, but we'll just cover a couple of slides before we get there. Okay, I don't know why these slides are particularly in this order, but anyway, the next few slides are about conditional branching instructions. You've already met a couple of them. Jump if no carry, and decrement jump if the number's 0. Sorry, if not 0. So the first one, you're basically doing a test on the carry flag. If the carry flag is 0, you do the jump. If not, you move on to the next instruction. The jump that you can do is actually only a small jump, as you'll see. So the next one we've done is one where you take one away, for example, from the accumulator, and then you do a test on it. And if it happens not to be 0, you can do your jump. If it is 0, you just carry on to the next instruction. And we used that one last week to actually write a little delay loop. To going around the loop, taking one away from the accumulator until it got to 0, and then we just carried on. But there are other conditional jumps. Jump if the accumulator holds 0. Jump if it's not 0. Conditional jump, compare and jump not equal. Now this is a very, very useful version of a conditional jump instruction. So what this is going to do is allow you to compare two 8-bit numbers. If they're not equal, you perform the jump. If they are equal, you carry on. I'll come back to this right at the end of today's lecture because this also has another very powerful feature associated with it. And you can see some examples here of these compare and jump and not equals. So here we're comparing the contents of the accumulator with the value 0f. So if the accumulator holds the value 0f, we don't jump. We carry on to the next instruction. If it does hold,
Jump if not.
If it holds 0f, we don't jump. If it holds anything else, we do jump. Okay? So compare and jump if not equal. So, yeah?
No, essentially finished.
Okay. Next one, you can see that this particular instruction can operate on other registers apart from just the accumulator. So here it's operating on register R4. So again, we're saying if register R4 contains decimal 35, then we would not do the jump. Any other value, we would perform the jump. And you can even use it with indirect addressing. So in this version of it, it's saying go to the register R1. What's pointed at by register R1, I should say. So we're not going into register R1, we're using that as an address to go somewhere else. When we get there, we're comparing the contents of that location with decimal 67. There are even more branch instructions, conditional branch instructions. So jump if the carry's set, jump if any kind of bit set, so you can test the bit on a board and do a jump based on that, conditional jump. Similarly, if it's clear and things like that. This is the point I wanted to make when I said that the distance you can jump is actually very short. The value that comes after the jump is only an 8-bit value, effectively a signed 8-bit number. That's how it's stored in the program memory. The biggest jump you can therefore do is either about 100, well, I'm kind of racing ahead here in a way, but if we're doing 8-bit signed numbers, the most significant bit is used to hold the sign bit. To basically say, am I jumping forwards or am I jumping backwards? Okay? If it's a 1, we're jumping backwards. That means a negative number. So 1 means the result is negative. If it's a 0, it means it's positive. The biggest positive number you can have is 3, 4, 5. Well, if you convert that, you're good with your binary to decimal conversion, you'll see that that's 127. The value 0 is 0, 0, 0, 0, 0, 0, 0, 0.